It's only pointing in this direction.
Alright, so you're recording yourself.
Recording myself, yeah. So hello everybody, my name is Naeem Chaudhary. I'm a first year master's student in the data science program here at New College, and I graduated with my degree in mathematics in 2018. So I want to talk to you about the style of this talk. I am going to be asking questions, okay? And in order for the talk to go smoothly, I need people to be willing to answer questions. I don't care who does it, as long as the questions are answered so that I can keep the talk going, okay? Now, for background, you won't need very much. So all I'm asking for is a little bit of Calc 1 and Calc 3. Okay, and what from those? You want differentiation, chain rule, the partial derivative, and the gradient. So of the things on this list that people are most likely to have forgotten, it's the gradient, so I'm going to talk about the gradient. Okay. Now, gradient. Let f be a function from Rn to R. So this is just an n-dimensional space of real numbers. You can think of them as points, n tuples. Okay. Then the gradient of f is a function from Rn to Rn. And I have to add this extra stipulation that it is scalar valued. That's what's meant by mapping to R, and differentiable. So the gradient is a map from Rn to Rn, where the gradient at a point x is the vector of its partial derivatives. Okay, and this is for some point x in Rn. Okay, so basically, given some point in n-dimensional space, you get some n-dimensional vector. Now, what's so special about this vector? What does it tell us about the function? Does anybody remember from Calc 3?
You better.
Yeah, like, oh, I forgot to mention, this is a judgment-free zone. We don't laugh at people's answers. Everybody gets stuff wrong. I get stuff wrong all the time. Okay. So, anybody want to take a shot?
I believe it's the point at which the function's increasing the fastest or decreasing the fastest.
Okay, so it gives us a direction, and the direction is in the direction of the steepest ascent, right? The fastest ascent. And also the magnitude of that vector tells us something about how much it's increasing, right? It's sort of like the equivalent of the slope. Yeah. So we have two things about it, that it's a direction of steepest ascent, and that its magnitude says like something equivalent to slope. Okay, good. So let's do an example. Let's say we have a function of two variables, and it's written as x squared plus y squared. What shape does this function have? Yeah, go ahead, Alex.
A parabolic.
Yeah, it's a paraboloid, right? And the way that we can think about that is we fix some x, right? And what's left is y squared shifted up by x squared, right? And then the same thing, we can fix y and then we'll have x squared shifted up by y squared. So you get something that looks a little bit like this. Please forgive my graphs. I'm not the best at them. Okay. Great. And I want you to help me compute the gradient. So what is the gradient of f x, y? Professors can answer too. That's fine.
I wouldn't want to bump one of the many students who could answer this question.
Yeah, like please jump on it because I really want the talk to keep moving, but I also want you to think I want you to be here while I'm doing the talk.
2x plus 2y.
Yeah, great. So it's going to be a vector with two elements in it, 2x and 2y. Okay? And if we wanted to evaluate at a point, let's say the point 1, 1, we just get a vector where we plug in the x and the y, and we'd get 2, 2. So if I were to plot this vector on this plane, right, we'd go to the point 1, 1, and then from 1, 1, we can draw a vector that has leg lengths 2 and 2. Okay? Now that tells us the direction of steepest ascent. But what if I wanted to know where the minimum of this function is? What could I do with that gradient?
Set it equal to 0.
Set it equal to 0, okay, and we can solve for where the gradient is equal to 0, and that'll give us, we would be looking for something with a magnitude 0. But let's say I'm blind, and I can't see, like all the lights are off, right? And I'm standing somewhere, and all I have is this gradient information. But I want to find the bottom of this bowl, right? Yeah, Austin.
You would look whether the magnitude is increasing or decreasing and adjust y and y and x accordingly to try to go towards where it's less.
Okay, yeah, so I think maybe what you're trying to get at is that I can talk about the point where I'm standing right now. Let's call it x sub n, right? And I can move in the opposite direction of the gradient. Since the gradient's going to the direction of the steepest ascent, we can move in the direction of the steepest descent, right? And we can call that new position x sub n plus 1. Now, there might be an issue here, so let's give it a shot. With this same point, we can say that x sub n plus 1 is equal to x sub n, which we decided was 1, 1, minus 2, 2. Okay, and that's equal to negative 1, negative 1. All right, so we just made a step. Great. Now, let's continue our algorithm and see what happens. So we plug in negative 1 into our gradient, and now we're going to get negative 2, negative 2. And if we follow our algorithm again, so the next point is going to be negative 1, minus negative 2, negative 2, and we're going to get 1, 1. So all we did was bounce back and forth between these 2 points. That's no good. Okay. So in order to solve this problem, we can tack on a coefficient here. And that'll change the magnitude of our gradient vector. Okay? And so we're stepping in this direction, and it has, this magnitude 2 squared plus 2 squared square rooted, right? I don't want to do arithmetic right now. Okay, and then you can shorten it or lengthen it by alpha, by a multiple of alpha. Great. And how do we do that? That is a class in all its own. I'm not going to talk to you about gradient descent right now, but it's a very important and rich topic that does not have a full solution. Cool. Does anybody have any questions for me so far? Nice. Okay. So, let's talk about an actual problem. We as humans like to predict things, right? We predict things because they will tell us when we're going to have the most amount of food. It's going to tell us whether or not we're going to make money, stock market. We can try to predict whether or not we'll win or lose, right? So in some ways, we collect data from the world around us, and then we try to classify it and put it into buckets, right? So this problem that we're going to be working on is a classification problem. And I'm going to work with an example in the beginning that a lot of us are familiar with, which is the OR gate. Okay, and can somebody help me fill in these values? So 0, 0, and 0, 0, 1, and 1, 1, 0, 1, 1, 1, 1, 1. Great. Let's try and plot this on a graph. So it's an XY coordinate. We have 0, 0, 1, 0, 1, 1, 0, 1. And the keen of us in this room actually know that there's a closed form solution to this problem. There's a function that we can write. We just take x and y and we add them together and subtract x times y. If you don't believe me, test it yourself. It does work. But again, we want to imagine a world where we don't know that perfect answer. Okay. So something we might want to do is take our xy plane and try to divide it up in such a way that all of the points that belong to one class, the true class, one class, are separated from those that are in the false class. So it might look something like this. Okay? Now, so this function, this line that I plotted is actually a very specific line. It's where the function that we're using to predict is equal to precisely 1/2. So given some points x, y, specifically the ones along this line, this function is equal to 1/2 here. Anything on the right-hand side of this function is going to be greater than 1/2 and therefore belong to the class that is 1. And everything to the left of it is going to belong to the 0 class. Good. So turns out that it's nice. With an OR gate, we can properly separate the truth values from the false values with a single curve. But what about if we're working with something different? So now I'd like to talk about exclusive OR. Okay, and it takes in 2 points x, y, and spits out another value. So, okay, again, I'm going to need your help here. 0, 0, okay, 1, 0, 0, 1, 1, 1, 0, right? So exclusive OR just means either one or the other, but not both. Great. And let's plot it again. Plot it. You know what that is. Now, can we use a single boundary line to separate the solutions on this plane? Given it has to be a function, right? So it has to pass the vertical line test. Can we do that? The answer is no, right? So there's no way, here are the true points, there's no way that I can divide up this plane so that it takes both and it's still a function, right? This is not a function anymore. And it makes this problem a little more difficult. Now again, the keen of us will know that there is actually a closed form solution to this, but we're pretending that we don't know this. Okay, and we want to use some iterative process to learn what the boundaries on this plane are.
But in that other example, you wrote it as a level set, like the 1/2 value for some function of x and y.
Mm-hmm.
And I can have level sets that do weird stuff, like bubble around points or whatever, you know, like a level set of a function of x and y. I mean, for example, this function, obviously, like, you know, equals a half will give us a curve. But you want specifically a function where y is written, you want y to be a function of x.
Yes, exactly.
Okay.
Good. Great. So now I would like to propose a way to think of, or a model by which we can approximate true and false values. And that model is the sigmoid function. So sigma of x is defined as 1 over 1 plus e to the negative x. Okay. And again, I'm going to need your calculus help. Let's help me draw this function. So I'm going to put a plane down. This is 0, 0. And tell me what to do so that we can learn about what this looks like. Anybody? I'll start making awkward eye contact. Okay, yeah, go ahead.
Let's think of what happens at the infinities.
Yeah, let's look at what happens at the infinities. Okay, so we take the limit as x approaches infinity of sigma of x. What happens to e to the negative x?
This is 0.
Yeah, it diminishes, right? And then we get 1 over 1 is 1. Okay, so we have asymptotic behavior in this direction. And as x approaches negative infinity, what happens? E to the negative x blows up, and we get 1 divided by some huge number is 0. Good. So now where does it cross the y-axis? 1/2, right? Great. It looks something like this. So I'm going to make the claim that this would be a great way for us to approximate truth values, because all of our potential values are sandwiched between 0 and 1. And once it crosses this boundary, we can just take it to be truth. But it also has a really nice property. Okay, so sigma of x, I'm going to write it as 1 plus e to the negative x to the negative 1. Okay, we're going to take the derivative together. So it's sigma prime of x is equal to negative 1 plus e to the negative x times negative e to the negative x, right? Chain rule, okay? And then we're going to get to negative 2. Y'all gotta call me out on that stuff. Sleeping, okay. And we'll have e to the negative x in the numerator and 1 plus e to the negative x squared in the denominator. That seems not much better than what we had before, but I'm going to make the claim that actually we can make it really simple for us, right? So if we do some tricky algebra, then we can rewrite this as 1 plus e to the negative x in the denominator times e to the negative x over 1 plus e to the negative x. Okay, what's this? That's just sigma of x. Great. Now, what's this? It's not immediately obvious, right? But what we could do is we could say, how about writing 1 plus e to the negative x over 1 plus e to the negative x minus 1 over 1 plus e to the negative x. This is just 1, and this is just sigma of x. Okay, so the derivative of the sigmoid function is just itself times 1 minus itself. Is that not a nice property? It's good. It means that things don't have to be complicated for us. Okay, does anybody have any questions? So another thing that I'd like to talk about is measuring error. And there's a standard way for us to do this. We say that the error is just the sum of the actual values minus our predicted values squared over the input values. Okay? So another way to think about this is that we have some table, right, with n many inputs, and there are n many outputs associated with that, right? So we can go through and maybe our sigma gives us 0.9 for the first one, right? So we subtract 0.9 from 0, right? And it gives us an error that we square. And we do that so that we don't have a negative error associated with the function. Okay? I'm going to do something egregious. I'm going to call this error epsilon because I'm a very hopeful person and I hope it's really small. We want to make it small. Okay, there. Typically this is written as RSS, but I don't want to write RSS. I want to write epsilon. Great. So we saw that the actually I'm gonna so now I want to talk to you about what neurons are.
But you don't wanna, why you don't wanna have error negative?
Why don't I want to have the error negative? Because we can sum the error. We can sum several errors that are high in magnitude in the negative direction and high in magnitude in the positive direction, and they'll cancel out to be 0, even though our actual error is much higher.
Okay, you wanna
Exactly. Great. Okay. So now I'm going to make less questions, and I'm just going to do some more declarations to get through some material that everyone or a lot of people is going to be unfamiliar with. I'm also going to use some slightly non-standard notation because I feel like it's better for teaching this topic. And then maybe when you go out and you learn about neural networks on the internet, you might see the diagrams presented in a different way. So I'm going to make a neuron. And this neuron is going to take in some inputs, x1, x2, that are just the values in a vector. Okay? And then there's going to be a constant that I'm going to call beta. Typically this is called the bias, and I'm going to set it to be equal to 1. And it's always going to be 1 for the sake of this problem. And we're going to do something with those 3 terms. And then we're going to feed it into our sigma function so that we can approximate a value between 0 and 1. And that's going to be our output. Now, question. How can we make sigma, which I only define here loosely in R, over R, to, how can we make it accommodate all of our variables? Right, so I want to plug in a vector into sigma, and I want it to do something and spit out a number in R. What can I do with that? It's a harder question. Go ahead.
Similar to the gradient?
Kind of. I don't think I'm posing the question in a very clear way. I guess what I want to say is that we want to take the vector and scrunch it down into R so that when we plug it into sigma, it actually gives us something in R again. So what functions do we know can do that? Yeah, go
Well,
ahead.
lots of stuff. I mean,
Yeah.
you could just take x1, but I assume you don't want to just
Yeah, I
do
don't
that.
want to do that. So I want to incorporate all of them,
Mhm.
right? So we could do the norm, right? I'm going to suggest a sum. Why don't we just sum them together, okay? So
That's
we
not
can do
norm.
x1 plus x2 plus beta, right? And we want to tweak our model in some way so that if we get these values x1 and x2 and we plug it into our function, it spits out the value that we want. Okay? So we can tweak them by tagging on some adjustable coefficients. Okay? These coefficients are called weights in the machine learning world, and they are what we control, so they're important. Okay? we're gonna control these weights to give us the model that we want. And I'm gonna call this function x of w. All right. Yes.
Can you explain what the beta is, what this function is?
Yeah. So beta is called a bias, and the best way that I can think about it, it's like if our, so let me write sigma here. Which I'm going to call 1. So it's kind of like saying, what effect, or what if none of our variables had any effect on the outcome? If we just had no effect and x1 and x2 were equal to 0, where would our boundary start? That's the way that I think about it. Okay. Great. So this drawing makes no sense right now, but I am going to argue that actually this drawing is representing what I've written here. Okay. So we take in a point x1, x2, and we plug them into this linear combination. And then we take that linear combination and we plug it into sigma, and then out of sigma comes some value between 0 and 1. This thing, in an ideal world, would predict what we want for the XOR problem. But this neuron by itself can only represent that single boundary line. So if we go back to our graph, we wanted to separate these points in such a way that these were in the same class together. And I'd like to suggest a situation where we have one boundary line like this and another one like this, and everything in between here belongs to the true class, and everything outside of it does not. So what we can do to solve that is make a network of these things. This is where the brain analogy really comes into play, right? You can think of a neuron with a activation value of greater than 0.5 as being turned on, as in shooting an electric signal, right? And it can shoot it to another neuron. So let's see what that looks like. So I'm going to repeat my drawing here. And I'm going to write the weights on these edges. And so I've got these two neurons, and they do exactly the same thing, right? They take in some values and note that they have different weights. So the way that they treat those values is different, and they're going to output something. And that output, I'm just going to feed into another neuron. Okay? And this neuron is also just a copy of the first two. And then we get a desired output. Okay, so this action of adding on another layer to the network, this is layer 1, layer 2, gives us this extra boundary line. Now, I'm claiming that without much explanation in the interest of time, but we should talk about it. I learned this in a class last semester, so there are things to learn from this, and undergrads can take the data science classes.
So just
Any
a-
questions?
Just a comment. So when I was talking before about the function versus level set, you did want it to be a level set, but you're just taking a level set of a very specific type of function, which is ultimately like a linear function of the variable. So it's always going to be a line.
Exactly.
You just use one of these things. But you're saying
Exactly.
plug more of them into each other, you can have more complicated.
That's right. And that's because linear functions are easier to compute, right? We want to do this on a computer. Great. Okay.
So you plot kind of curves there, those should supposed to be line, right?
Yeah, I mean, a level set of a single neuron for any set of weights is just going to be some line.
Right.
Somewhere. It could be vertical, but yeah.
Okay, so now we have a new output function, and that output function I've written here as sigma 3. Okay? And sigma 3 takes in as its argument f sub 3. So it looks something like this. Yes? Good. Now, we're trying to make our predictions accurate. So what do we want to minimize here?
Yeah.
We want to minimize the error, right? So we take in one input and we measure it against the actual, we measure the predicted response against its actual response and square it, and it'll give us part of our error, right? But we want to actually sum up the residual squares for all of the inputs. So this extra one here, that's for indexing over our input data. So let's take it back to our problem so this doesn't get confusing, right? So we have 4 data points in the XOR. We have 0, 0, 0, 1, 1, 0, 1, 1. Okay. We plug in 0, 0, and it gets multiplied by these weights and added up in this function, put into this sigma. That sigma gets put into F3. F3 gets put into sigma 3. Sigma 3 outputs some value between 0 and 1. Let's say 0.7. Now the actual value that it should take on is 0. So we do 0 minus 0.7, and we square it. And then we go on to the next input, right? We do 0, 1, do the same thing, making sure that we put it in both neurons. Out comes some predicted value, and in the end, we'll get some real value, which is our error.
This is for some given set of weights. We start out with some set of weights.
Right, exactly. So we start out with some set of weights. You can make them randomly, or maybe you can make them with some smart decision, knowing that you might be close to the, well, I don't want to give away the story there, but it's coming soon. So let's look at what computing, or what minimizing the error looks like. Okay, we have a function. That function is, I called it epsilon, right? And it's the sum of the errors squared. And let's say this is I, this is I. Question. What does epsilon map from to get to R?
What do you use?
It's going to be the W's, and the W's live in, yeah, it's 9-dimensional space, right? So we're trying to tweak these weights in such a way that they give us the desired output. And the error is a function of those weights. There's 9 of them, so we're in 9-dimensional space, and we map it down into R. And we want to use what to minimize this function? It was earlier in the time. Yeah, Austin. The gradient, right? We want to take the gradient of this function. So we want to compute the gradient of epsilon, which is the vector of its partial derivatives. So del epsilon, del W1, del epsilon, del W2, del epsilon, del W9. And let's try to compute one. So we're going to do the easier one first. I want us to compute del epsilon del weight 9. So remember that sigma, or, remember that epsilon looks like this. And so what if I were to take the derivative of epsilon with respect to sigma 3? What would that look like? So we just pretend that sigma 3 is our x, our variable, right? And everything else is constant. So this is just a linear combination of functions. And so we can pull down a 2, right? And then make it a 1. Everything else stays the same. And then we multiply by the derivative of the inside, the chain rule, right? And that's going to be negative 1. Okay, good. So this part is going to be 2 sigma 3 minus 1. So, everybody buy that? Good. Okay, and then what about the derivative of sigma 3 with respect to f3? What's that look like if we're looking over here?
You should have summation, right?
Yeah, there's a summation.
There's your formula from before.
Yeah, right, so we took the derivative of sigma and it had this really nice property where it was just itself times 1 minus itself. Great. That's wonderful for computing because we have sigma 3 stored in some variable and we don't have to take it and do some stuff with it to get the derivative. It already exists. Cool. And then we can multiply by the derivative of function, or f3, and weight 9. And I'll write this down for you just a second. Okay, so what's the derivative with respect to weight 9? 1, right, good. So this is just times 1. And we can call that del epsilon del weight 9. Not bad, right? There's a lot of indexed variables, so it kind of looks intimidating in the beginning, but it's not so bad until we look at a little bit longer computation. Oh, by the way, what am I abusing here? What did you guys call this when you learned this? This way of dealing with the chain rule? I call it the middle school math rule. Right? You can just sort of like cancel out the numerators and the denominators and get what you want. It's not really working like that, but this is how you can think about the chain rule. It makes it a lot easier. Okay. Great. So we're going to start this process with the same thing, right? We're going to take the derivative of epsilon with respect to sigma 3, multiply it by the derivative of sigma 3 with respect to f3, and this is where things change a little bit. Now we want to get all the way down to weight 1, right? And currently we're here. So what's the next partial derivative I want to deal with? Yeah.
Sigma 1.
Yeah, exactly. So it's the derivative of sigma 1, or excuse me, f3 with respect to sigma 1. Good sound. All right, and now we're in sigma 1, so we can just take the derivative of sigma 1 with respect to f1, and finally the derivative of f1 with respect to w1. I argue that this is just as easy as the last thing I did. It's just longer. Okay. This is the same. This is the same. Now, the derivative of f3 with respect to sigma 1, what's that? One more time?
W7.
Yeah, weight 7, right? Derivative of sigma 1 with respect to f1? It's sigma.
1.
Yeah, it's sigma 1, 1 minus sigma 1. And then derivative f1 with respect to weight 1. I know f is not written on the board here, but you can kind of make it look like this.
X1.
It'll be x1, right? Because here instead of a sigma 1, there's going to be an x1. Okay, so
Yeah, it's summation.
yeah, there's a summation. Thank you. Okay, so we do this 9 times, and we're going to get a vector. And that vector is going to be in the direction of steepest ascent. But we don't want to increase our error, we want to decrease it. So we start at some set of weights. I'm going to call it W sub naught. And we want to subtract.
Maybe with a vector, so we're not confused.
Yeah, thank you. W sub naught. Yeah, that's a good point. Thank you. And we're going to subtract the gradient of f at the gradient of epsilon at W sub naught. But again, we can run into that problem that we did with the paraboloid. So we want to tag on some coefficient so that we can stretch and shrink that step. And that is the new position that we're at. So I just explained to you the very basics of neural networks. It's just Calc 3. It's not bad. And it's really powerful. It can do a lot of things. It's really fun to program on your own too. If you want to tackle this problem, you know, it's a pain, but it's fun when you're done. Does anybody have questions? Yeah.
So do you just choose something for alpha, or is there like a way you want to like scale it?
Really good question. So there exist algorithms that help you choose that, and they're called line searches, right? So you have you're at a fixed point, right? You've already fixed all your weights, and then what you do is you meet some criterion that allow your alpha to be maximal, to be like optimized, right? What are some problems that we can have in minimizing this error function, by the way? It's related to the alpha.
Well, there's local minimum. I mean, if you're trying to find a global minimum, you might get stuck in a little
Exactly.
local minimum.
Yeah, so our function, might look something like this, just, I don't know, in W9, in R9. And let's say we start here, right? Well, our minimization process is going to take us here when the global minimum is actually here. You see that? And so one of the things that we can do with our gradient descent is add some random perturbations so that we can accidentally step sort of in the wrong direction, but then maybe it'll take us on the right track to the global minimum. Any more questions?
So in practice, there's some scheme where alpha is like dynamic, is changing throughout the process, and sometimes it's
Exactly.
bigger than one, sometimes it's smaller than one. And
Exactly. So we have W naught, and then we compute the gradient, and then at this step, once we have both of those things computed, we pass on to another algorithm that chooses the step size, and then we choose the step size, and then we reiterate the process, and that's called a line search.
so one more question. Once we've trained this, I don't know if you have the numbers, the W's for XOR, but could you maybe, what does the boundary curve look like? The 1/2 boundary curve that classifies XOR?
I don't have that with me. That's a really good question.
That does an exercise for the class.
But it looks a lot like sort of what I drew. It just, there are so many solutions that will make the classification properly, but might not be the maximal, the optimal solution.
Do you have any remarks on computational efficiency? Because I mean, just with 2 neurons, it seems like we're doing a lot of computation.
Yeah, that's why linear algebra and matrices are our friends. Yeah, they make a lot of that much easier for us. That being said, there's a lot of computational complexity in this problem that we can deal with, for instance, in the gradient descent process. If you were to perfect your line search, it actually makes your gradient descent worse because what you're doing, right, is you're going to step in a direction and then let's say you try to find the lowest point in that direction, right? You're there. So along this axis, you've already found the lowest possible point. So when you do your next gradient, it has to be orthogonal, right? And so if you're taking orthogonal steps to some center, I'm really bad at drawing these. I'll try my best. Then it takes longer than maybe adding some random perturbation to it and going in this direction, and then maybe the gradient will take us here, and then maybe the gradient will take us here. Right, so there are several different ways of doing this. One of our professors does research in one called stochastic gradient descent, Dr. Kalmanovich. So if you ever want to work with him on that, it's an option. Okay.
There are other algorithms though, right? Is there any particular reason why you use gradient-based method to minimize that function?
The only answer I have for that is that that's what I learned. I'm curious about what other kind of.
Like genetic algorithms, for example,
What kind of genetic algorithm? I
Yeah.
haven't learned about.
or Monte Carlo
Like-
Markov.
Oh, yeah, the Markov chain.
Yeah.
Okay. Thank you very much, everybody. Yeah. Thank you. Sorry, actually, Austin had a question. Oh, sorry.
I was just gonna ask, we were talking about using randomized changes in like the learning rate.
Mm-hmm.
Do you mean changes of like, say like 0.05 to 0.5 or like 0.05 to like 0.03? Like how big
The
of a
learning
change?
rate being the alpha, the step size. So it turns out that alpha can take on any positive values, and the restrictions on those values involve. So you take a cross section of the function that you're trying to minimize. Okay. And you use some information to decide that whatever your step is meets some minimum requirement where the slope is steep enough, but also not too steep, and then that creates a boundary for your alpha
I
values.
gotcha. So there's like a restriction so you don't skip over.
Exactly. Yeah, they're called the Wolf conditions. I want to write them down for you, but I don't like making mistakes on the blackboard. So.
Thank you.
Okay,
Is
great.
this basically always the model for a neuron, and then you just connect them? And I mean, they can be more number of inputs, but they're always just some like linear combination, and then spit it into a sigmoid. That's a neuron.
The answer is no.
Okay.
There's a better function than the sigmoid called the Rayleigh function. Yeah, that I haven't spoken about yet, but activation looks a little bit different in that world. Professor?
No, you can choose a different sigmoid, but you really want to try to preserve the linearity because you have lots of tools.
Right.
Exactly.
Yeah.
So you want this back propagation is going to be pretty robust as
Right.
long as you're actually solving it.
And what I should have mentioned is this process here of computing the chain rule, that's called backpropagation in the machine learning world, deep learning world. Now I'm going to stop for real. So let's stop.
So you learn stuff in that in